we're going to the next talk, and we're going from the ocean to sea ice. And this is Skylar from Caltech presenting on Subzero.jl.
Thank you. Hi, everyone. So yeah, my name is Skylar. I'm a research software engineer at Caltech in Dr. Andy Thompson's lab. And so today I'm going to be talking to you about Subzero.jl, which is a not yet released, but in the future soon to be released package for discrete element sea ice modeling, which I'll go into what that is a bit more in a second. And this talk is going to kind of have three stages. The first talk is just what is discrete element sea ice modeling, what is this model Subzero, and then our successes and challenges on moving what was originally a MATLAB model into Julia. And so jumping into the background, I'm going to start by sort of introducing the team that I work with. So I work with Andy Thompson and Mukund Gupta at Caltech. They're my advisors on this project. And then Mukund and I are co-mentoring Rohais Harris, who is an undergraduate from Georgia Tech using Subzero.jl to start performing some real science. And the original authors of the model in MATLAB are Gheorghe Manoucharian and Brandon Montemuro at University of Washington. And all of this is funded under a multi-university research initiative from ONR, which is Mathematics and Data Science for Improved Physical Modeling and Prediction of Sea Ice. So from that background, and kudos to my lovely team. So why are we looking at discrete element sea ice modeling? As you may know, we're losing ice. So this is the Arctic sea ice extent from 1980 to 2020. We have this sharp downward gradient. It's not looking good. But the thing is we're not actually losing ice everywhere in the sea ice pack equally. We're losing ice around the edges of the pack, which you can see in the more colorful figure in the dark blue around the edges. And these edge zones, sort of where the sea ice pack meets the ocean, are what's called the marginal ice zone. And in this marginal ice zone, it's not actually one big sheet of ice. What we see are individual ice floes. That's F-L-O-E. And so I'm going to use that word a lot, and I mean ice pieces. And basically, the amount at which these ice flows look like individual chunks versus a big pack sort of depend on seasonality and conditions, but in this marginal ice zone is where we see the highest occurrence of individual flows. And so the question is does this looking completely different from one big ice sheet, which is what's represented in most big climate models, does that impact dynamics in these critically important regions which have the most melting? And so that's really where discrete element sea ice models come in, which represent each flow individually in order to study dynamics. And so this is the model that we're working with. This is Subzero. And basically what Subzero does is every ice flow is a polygon. We can have convex or concave, and in the top you can see different configurations with different percentages of sea ice, 30, 90, 100. And in this little cutout, you can see both convex and concave flows. And the other thing about Subzero is that these flows actually change size, and we change magnitude of flows throughout the run. So depending on conditions, flows that are overlapping and interacting can meld together through welding. Overlapped areas can sort of be transferred to one flow or another, and if put under enough stress, the ice will crack and split into multiple new flows. And again, this was written originally in MATLAB by Gheorghe and Brandon. And so with that background, I want to show you a simulation run by Subzero. And so I want you to first focus on this panel that is closer to me. I'm just going to play this and talk through. And so this is the Nares Strait, which is an important channel for sea ice transport. And it's quite narrow. And so the thing is that in global climate models, this isn't resolved well because it's 1 or 2, 3 grid cells, especially in width. But the thing is this is actually critically important for the state of Arctic sea ice. And so what we're seeing here is a downward flow pushing these individual ice flows downward. They're cracking as they move throughout the strait. So let you guys see that for a second. And I'm going to play this one more time, and I want you to focus on the other side. And what you can see here is there are actually 4 small islands. So there's 3 right here and 1 up here. And that is actually the correct formations that are in the actual Nares Strait. And so this actually allows us to look at how these 4 perhaps seemingly inconsequential islands give us a new idea of how ice dynamics work. And we can see that this actually causes the ice flow to move much slower throughout the strait. So this is the type of experiments that people are starting to do with Subzero. And Gheorghe and Brandon are actually busy comparing this to satellite imagery so we can assess the performance of the model with an eye towards realism. So I'll just let that finish, and then we'll move on. Okay, fantastic. So let me move forward. Okay, so with that, that's sort of the model in MATLAB, and we've been working for a year on translating it to Julia, and our eye for translating it to Julia is threefold. So the first is really performance. As you can imagine, this is a rather costly model representing all the individual flows. And so improving performance will allow us to run bigger, more complex experiments. The other is coupling. A big reason we want to look at this is we want to look deeper at how the ocean affects the ice, but also how the ice affects the ocean and eventually the atmosphere. And then finally is just an eye towards making this more open source, moving away from MATLAB, and also just making the model more usable for scientists in general. And so this is sort of how we're doing on these three fronts. Performance is definitely improving. So this is a shear flow simulation, which basically means that at the 50-kilometer mark, right through the middle, we have 0.5 meter per second flow, and then a gradient up to 0 meters per second at the top and bottom, pushing ice flows. And here we have performance MATLAB versus Julia in minutes. Flip the axes, my bad. We have 25, 50, 100, 200, and 400 flows, and we're actually seeing improvements of up to 25 times speed up. And this is through a combination of just the straight translation and then profiling the code through memory and speed profilers and just sort of picking off the low-hanging fruit. And we're confident we can actually get more performance out of this model. So this is already a huge win. The other thing is coupling. So we've been working on coupling with Oceananigans, which you just heard about. We've successfully coupled both one-way and two-way with Oceananigans, which means one-way is the ocean affecting the ice, and two-way is ocean affecting ice, but also ice affecting the ocean. And so we're working on that. This is a one-way coupled GIF, but we're running preliminary experiments now. And the next step could potentially be to couple to an atmospheric GCM, perhaps ClimateAtmos, in the future. And then there's potential discussion of making this coupling more streamlined for future users, trying to take advantage of the coupling framework that's being set up within Klima. And then just a quick touch on the coupling. Sort of the way that we're doing this is it has to be grid cell by grid cell. And our eye is to make this precise because we really want to study how exactly ice flow and ice movement is affecting the ocean. And so basically we have what we're calling subflow points, at least one per grid cell. It's sort of up to users how to define, and we have several schemes for defining subflow points based on user wants, and more could be extended. And then through that, we're able to calculate the stresses ice to ocean and ocean to ice and pass that into Oceananigans as a field to continue our runs. And then the other big win is just distribution. So in this switch to MATLAB, there's been significant code redesign, and we've really taken inspiration from Oceananigans' setup of having a simulation which holds a model, holding all the sort of necessary components for a run, physical constants, output writers outside the simulation. And so this has really led to increased modularity, and really multiple dispatch has been a huge win here. In original Sub-Zero in MATLAB, to make a new simulation with different boundaries, we actually had people had different versions of the model entirely saved with different boundaries, or huge chunks of code in multiple files that needed to be commented in and out just to make these changes. But here, through multiple dispatch, a lot of the switches to make different types of runs just become seamless. It's a huge win for us in Julia. And we're planning a release of Sub-Zero.jl sometime in the future. Now on to the challenges. And the two that I really want to touch on are the geometry environment and sort of the state of that in Julia at this time, and also a parallelization strategy. So choosing the best option for our evolving discrete elements, as these are things we're working towards in the next year. So the first is geometry is kind of tricky in Julia, actually. And the library we use right now is called libgeos, which is just a wrapper for geos, C-API. We picked this because it's really robust. It has all the functionality that we needed, which after scrolling through pages of Julia geometry libraries wasn't something that was readily available in other libraries, just because it is a new language, so we don't have that robustness that things like Python have. But through further use, you kind of find out, this isn't quite type stable, and it's leading to quite a lot of excess allocations. And this is not to shame libgeos, type stability in geometry is quite hard, because if you pass two polygons to an intersection function, you can get any number of outputs, another polygon, a line, a point, nothing, a multi-polygon, and this is quite difficult for Julia to handle. without, code-worn type going crazy. And the other is sort of excess allocations. And this is more because it's a C library and dealing with pointers and these polygon objects, and we're dealing with coordinates. And it turns out that these polygon objects are not quite thread safe. So this leads to excess allocations at the moment. And so we're really looking to move away from libgeos. And as sort of a show of how much we think this will actually improve performance further, this is a memory allocation. If you all look at this huge yellow line in the middle right here, that's from making polygons to pass them to these functions. So once we're able to get away from that, which is, as of profiling, one of our #1 priorities, we expect to further speed up. And so finally, on the geometry side, this sort of my confusion at what to do in this geometry led to a conversation on the Slack channel. Shout out to the lovely people in the geometry channel. As you can see, this led to an almost 100 reply chain of messages with me saying, hi, all these bullet points are libraries that I've considered using. None of them are quite right. And everyone was like, that is very true. Which felt very vindicating. And so we've started this new library called geometryops.jl. And so the idea is to unify these different packages, hopefully sort of unify the geometry community to put all the wonderful methods that are spread across 20 different packages into one package, make it what's called geo-interface, which is something in the geometry community to allow sort of different types of shapes built in different ways to work with the same functionality. And we're focusing primarily on 2 and 2.5D geometry. So if anyone loves geometry, hit us up because we're slowly starting development on that. And then the other big thing that I want to touch on is parallelization strategy. And so the question here is what's best for this type of problem? Multi-threading or distributed? And right now we have multi-threading over both flows and grid cells, sort of depending on the computation that we're doing at the time. And this has advantages in that a lot of these computations are sort of flow by flow. We're moving individual flows. But we have this problem that many computations, such as merging 2 flows, affect 2 flows at once, and multiple flows can be affecting multiple other flows. And so we're having to jump out from parallelized to serial all the time. So that sort of leads to, distributed, great. Flows that interact with one another are close to one another. But the problem is we have these flows that will inevitably cross over these regions. And because they are in fact one object, they need to maintain very close communication. We can't have them moving in different directions. And so this leads to perhaps, I'm not super well-versed in this, and so I welcome feedback. This seems like it could present a problem. And so basically, we are looking to redesign this parallelization scheme to continue to optimize performance and would welcome feedback. And that sort of leads into our other question. Right now, we're on CPUs, but obviously, we couple with Oceananigans, which is on GPUs. And so we were wondering if that might be something that would be well-suited to this problem, and it's something we've started researching, but would welcome feedback on either of these points. So thank you. Yeah. Yeah, so there's a couple.
I think we should probably repeat the questions, right?
Oh, absolutely. Yeah. So the question was sort of how do you set up the ice flow field? Do you pick a random assortment of polygons? There's 2 sort of ways to initialize a field. That is sort of one of them, but what we use is called Voronoi tessellation. And so basically it will fill an empty space with a subset of polygons, sort of filling the whole space. There's also the option for those different percentage fullness, and by doing that, we just sort of remove elements from the Voronoi tessellation. You also can read in flows from a file, so if you had perhaps, let's say, a satellite image that you wanted to model, and you could use computer vision techniques to sort of get the coordinates, that could easily be read in and simulated. Yes?
You're basically 2D, so you wouldn't
Correct.
cover in a river if the ice pack would run one under another one.
Yeah, so we are 2D. There is functionality for ridging and rafting in the original, which basically says that if they overlap to a certain amount, we just sort of prescribe that overlap area to one flow or the other, and then adjust the height of the flow to match, sort of to keep the mass balanced. Yeah, and that is not currently in the Julia, but it is in progress in the translation. Mm-hmm. Yes. Oh, sorry. Mm-hmm. No, continue.
Just complimented because from idle electric stations, sometimes you have ice buildups.
Mm-hmm.
And I was wondering if you could simulate.
Not Not yet, not yet. It's definitely a consideration of how much we want to take into account height in the future, and it's an open conversation. Yeah.
When you're doing coupling of the flows with the ocean
Yeah.
itself, that must, I'm trying to understand that this is general to the whole picture where you show ocean and, atmosphere,
Yeah.
all this stuff. To do those simulations separately and then to couple them, you must be doing explicit time stepping in each of them and having feedback from the previous guys.
Yes. Yes, and that's something sort of right now we have a very basic coupling scheme where we in a for loop we take a couple of time steps of our model, we take a couple of time steps of Oceananigans, and we pass basically right now just the stress field back and forth, and we're going to increase the amount of fields, so there'll be temperature and salinity and those sorts of things as coupling progresses. But yes, right now that is sort of how we're doing it. Correct. Yeah. Correct.
Which, if I understood you correctly, would also suddenly drastically increase the computational demand that is
Correct.
net.
Yes.
So how do you know if you, let's say, start with a certain flow distribution, you press play in your model, how do you know how many flows that you're going to produce, and therefore how long your model is basically going to run in the future? Or is there basically at some point a hard cap that you say, we want to be able to simulate this, and every flow that is smaller than X is deleted or something?
Yeah, one of the banes of my existence is the lack of knowledge of how many flows you're going to have. And so that's sort of an open question when you started. I mean, you can make guesses sort of based on, you can pick different fracture criteria and set different parameters, and this will affect how quickly everything is fracturing. And there is also a lot of settings. So for example, minimum flow size, at which point flows will be deleted. That way you're not, modeling infinitesimally tiny flows and just slowing everything down. But that is a problem we're grappling with, and that's something I actually grapple with a lot with saving data, never knowing exactly how much I'm going to need and non-square matrices and all of these problems. So another open challenge. Yeah.
Yeah, that sounds... Is that also on?
No, it's not.
It's on for the web.
Now it's on? Okay, so it's just on for the... Okay, now I get it. It's just
okay.
on for the live people. Yeah, I guess then it's also really the problem if you go onto GPUs because you don't necessarily know how much memory you already have to allocate.
Yes, yeah. Yes, pre-allocation becomes quite tricky. That's something you sort of, I'm thinking about in ways to decrease memory usage because you never, at any given time step, know exactly how many flows you have. And there's both increasing numbers of flows, but also you lose flows every time step due to various things. So it's tricky.
Very tricky. Do we have another question? One more? That we have time? Now we have a microphone.
Are flows only created by fracturing, or also can they be spontaneously formed out of the ocean?
Yeah, so with the right thermodynamic conditions, they can be spontaneously formed. That's another feature that's still being moved from MATLAB into Julia. But the idea there is very similar to the Voronoi tessellation. So you'll just retessellate open areas with the right thermodynamic conditions, and then they'll have a very low height to sort of represent brand new ice.
Oh, and then height can sometimes grow.
Yeah, height can increase or decrease based on thermodynamic conditions. So you'll see that growth.
Cool.
Yeah, thanks.
What were the easiest and hardest parts of translating from MATLAB to Julia?
I mean, I think the actual translation of particular functions is not too tricky because, I mean, the great thing is they're both one indexed. So that's one problem. This is one problem where you don't get lots of little bugs in the indexing, at least. But I think the hard part is there is that desire just to do the direct translation because it can work, but the structure needs to be completely different to have performant code. So it's sort of fighting that urge for speed versus speed of translation versus quality and performance of code. Yeah.
Amazing.
Thank you.
Thank you so much, Skylar, for presenting.